Hello there, and welcome. I'm so glad you're here with me tonight. Maybe you've had a long day. Maybe your mind has been racing with thoughts that won't quiet down. Maybe you're just looking for a gentle place to rest while the world outside keeps spinning. Whatever brought you here, you're welcome, you're safe. And for the next little while, we're going to drift together through something vast and beautiful. Tonight, we're talking about time and space. But we're not going to rush through facts like we're reading from a textbook. No. We're going to let them wash over us like waves on a shore. We're going to explore the universe the way you might explore a dream, where one idea flows into the next, where wonder and curiosity mix with the deep calm of knowing that we're part of something so much bigger than ourselves. Tonight, we're not just learning about time and space. We're drifting through them. We're letting them hold us the way the night sky holds the stars. We're remembering that we're made of the same stuff as distant galaxies, that we're connected to everything that has ever been and everything that ever will be. In every fact I share with you, there's an invitation to wonder, to dream, and to rest. So let's begin. Let's step out into the darkness together, knowing that even in the deepest parts of space, even in the strangest corners of time, there's beauty waiting for us. There's peace, there's home. Are you ready? Then let your mind drift. Let go of the day behind you. And come with me into the gentle mystery of time and space. Fact 1. Space is not completely silent, but it's close. There's no air in space, and sound needs air or water or something solid to travel through. So if you could float out there between the stars, you wouldn't hear anything at all. No wind, no voices, no hum of distant traffic. Just perfect, absolute silence. It's the kind of quiet that makes you aware of your own heartbeat, your own breathing, the small sounds inside your own body that you usually never notice. Fact 2, time feels steady to us, like it's always moving at the same speed. 1 second follows another, 1 minute after that, 1 hour after that. But time isn't actually the same everywhere. If you could travel really fast, close to the speed of light, time would slow down for you. You could take a journey that feels like a few years to you, but when you came back to Earth, decades might have passed. Your friends would be older. The world would have changed, but you would barely have aged at all. Fact 3. The universe is about 13.8 billion years old. That number is so big it's hard to imagine. If you tried to count to 13 billion, and you counted one number every single second without stopping, it would take you more than 400 years. The universe has been around so long that the light from some stars has been travelling toward us since before humans existed, before dinosaurs walked the Earth, before Earth itself was even formed. Fact 4. When you look up at the night sky, you're looking back in time. Light takes time to travel, and the distances in space are so enormous that even light, which moves faster than anything else we know, takes years or centuries or even millions of years to reach us. The light from the sun takes about 8 minutes to get to Earth, so when you see the sun, you're seeing it as it was 8 minutes ago. The stars you see at night might be showing you what they looked like hundreds or thousands of years in the past. Some of those stars might not even exist anymore. Fact 5. Space is expanding. The whole universe is getting bigger, like a balloon being blown up. Galaxies are moving away from each other, and the farther away a galaxy is, the faster it seems to be moving. This doesn't mean galaxies are flying through space. It means space itself is stretching. It's like if you drew dots on a balloon and then inflated it. The dots don't move across the balloon's surface, but they get farther apart because the surface itself is expanding. Fact 6. There's something called the speed of light, and nothing can go faster than it. Light moves at about 186,000 miles per second, or about 300,000 kilometers per second. That's fast enough to circle the entire Earth more than 7 times in just 1 second. But even at that incredible speed, it would still take light more than 4 years to reach the nearest star outside our solar system. The universe is just that big. Fact 7. Time didn't always exist. Before the Big Bang, which is the moment when the universe began, there was no time. There was no space either. There was no before. It's one of those ideas that feels impossible to wrap your mind around, and that's okay. It's a mystery that even scientists sit with in wonder. Time and space were born together in the same instant, in a burst of energy so powerful that it's still echoing through the universe today. Fact 8. Black holes are places where gravity is so strong that nothing can escape, not even light. If you got too close to a black hole, you would be pulled in, and time would do something strange. As you fell toward the center, time would slow down for you compared to someone watching from far away. To them it would look like you were frozen, moving slower and slower, never quite reaching the edge. But from your perspective, you would fall in quickly. Time itself bends around black holes. Fact 9. The Earth is moving through space right now, even though you can't feel it. It's spinning on its axis, which gives us day and night. It's also orbiting around the Sun at about 67,000 miles per hour, and the Sun itself is moving, carrying the whole solar system through the Milky Way galaxy at about 500,000 miles per hour, and the Milky Way is moving too, drifting through space along with billions of other galaxies. We're all in motion, all the time, dancing through the universe. Fact 10. There are more stars in the universe than grains of sand on all the beaches on Earth. Think about that for a moment. Every handful of sand, every beach you've ever walked on, every desert, every shore. Now imagine all of that, and know that there are more stars than those tiny grains. Each one of those stars is a sun, and many of them have planets orbiting around them. Some of those planets might be like Earth, some might have life. The universe is almost unimaginably full. Fact 11. Time zones exist because the Earth is round and spinning. When it's daytime where you are, it's nighttime on the other side of the planet. We divide the Earth into 24 time zones, one for each hour of the day, so that noon happens when the sun is highest in the sky no matter where you are. But time zones are a human invention. Time itself doesn't care about borders or clocks. The sun rises and sets in its own rhythm, and that rhythm has been the same for billions of years. Fact 12. There's a place in space called the cosmic microwave background. It's a faint glow of light that fills the entire universe, left over from the Big Bang. It's like the afterglow of creation, still warm after almost 14 billion years. Scientists can detect it with special instruments, and by studying it, they can learn about what the universe was like when it was very young, just a few 100,000 years old. That light has been travelling through space ever since, carrying the story of the beginning. Fact 13. If you could somehow survive the cold and the lack of air, and if you floated in space far away from any stars or planets, you would see darkness like you've never seen before. But it wouldn't be completely black. There would be tiny points of light everywhere you looked, more stars than you could count in every direction. And if you waited long enough, your eyes would adjust, and you would start to see faint glowing clouds, nebulas where new stars are being born, and distant galaxies shining like jewels. Fact 14. The moon affects time in a small way. The moon's gravity pulls on the Earth, creating tides in the oceans, but it also pulls on the Earth itself, creating a tiny bulge. This bulge creates friction, and that friction is slowly slowing down the Earth's rotation. Millions of years ago, a day on Earth was shorter than it is now. In the far future, days will be even longer. The moon is also slowly drifting away from us, about 1.5 inches every year. One day, far in the future, it will be much farther away than it is now. Fact 15. There are planets in our solar system where time feels different. On Jupiter, a day is only about 10 hours long because Jupiter spins so fast. On Venus, a day is longer than a year. Venus takes longer to spin once on its axis than it does to orbit all the way around the Sun. If you stood on Venus, you would see the Sun rise in the west and set in the east, because Venus spins backward compared to most other planets. Time and space create endless variety in the universe. Fact 16. Light from the Big Bang is still reaching us. The universe started as something incredibly small and incredibly hot, and then it expanded and cooled. For a long time, the universe was so hot that light couldn't travel freely. It was trapped, bouncing between particles. But eventually, the universe cooled enough that light could move through space. That first light, from when the universe was about 380,000 years old, is what we see in the cosmic microwave background. We're still bathed in the light of creation. Fact 17. Space is mostly empty, but it's not nothing. Even in the darkest, most distant parts of space, far from any stars or galaxies, there are still tiny particles popping in and out of existence. They appear for just a fraction of a second and then disappear again. Scientists call these virtual particles and they're part of the strange rules that govern the smallest parts of reality. Even emptiness has energy. Even silence has a hum we can't quite hear. Fact 18. If you travelled at the speed of light, time would stop for you completely. This is one of the strange truths that comes from the way the universe works. As you move faster, time slows down. And if you could somehow reach the speed of light, which is impossible for anything with mass, time wouldn't pass for you at all. You could cross the entire universe in an instant from your perspective, but to everyone else, millions or billions of years would go by. Time and speed are connected in ways that seem magical but are written into the fabric of reality. Fact 19. The sun is enormous. It makes up about 99.8% of all the mass in our solar system. All the planets, all the moons, all the asteroids and comets, they're just a tiny fraction of what the sun is. And yet, compared to other stars in the universe, the sun is just average. There are stars hundreds of times bigger, stars so large that if you put one where the sun is, it would reach past the orbit of Mars or even Jupiter. The universe is a place of scales we can barely imagine. Fact 20. Time can be measured in so many ways. We have seconds and minutes and hours, which come from ancient Babylonian mathematics based on the number 60. We have days, which come from the Earth's rotation. We have years, which come from the Earth's orbit around the Sun. But we also have geological time measured in millions of years, and cosmic time measured in billions. And then there's personal time, the way a moment can feel like forever when you're waiting, or how a whole afternoon can disappear when you're lost in something you love. Time is both absolute and deeply personal. Fact 21. There's a point in space called a singularity, found at the center of every black hole. It's a place where all the matter that fell into the black hole is compressed into a space smaller than an atom, maybe even infinitely small. At a singularity, the laws of physics as we understand them stop making sense. Time and space become twisted into something we can't describe with our current mathematics. It's a place of pure mystery, where the universe keeps its deepest secrets. Fact 22. The Milky Way galaxy, which is our home, contains between 100 billion and 400 billion stars. It's shaped like a spiral, with long arms of stars and gas swirling around a bright centre. Our sun is located about halfway out on one of those arms, in a fairly quiet neighbourhood. If you could see the Milky Way from outside, from far away in space, it would look like a beautiful pinwheel of light, slowly turning over hundreds of millions of years. We live inside that pinwheel, looking out at the rest of it from our small corner. Fact 23. Time travel to the future is possible in a way. If you could travel very fast, or if you spent time near something with very strong gravity like a black hole, time would pass more slowly for you than for everyone else. When you came back, you would have travelled into their future. You would have aged less than they did. This isn't science fiction. It's been proven with extremely precise clocks on airplanes and satellites. Time really does move at different speeds depending on how fast you're going and how strong the gravity is around you. Fact 24. Space smells like metal and burnt steak, according to astronauts who have been there. When they come back inside from a spacewalk, their suits carry a smell with them. It's probably from dying stars, from high-energy particles that have travelled across space and stuck to the fabric. It's the smell of the universe itself, sharp and strange and nothing like anything on Earth. It's a reminder that space is a place, not just an idea, and it has textures and scents and qualities that we're only beginning to discover. Fact 25. Every atom in your body was made inside a star. The hydrogen in your water, the calcium in your bones, the iron in your blood, they were all forged in the nuclear fires at the hearts of stars that lived and died long before the Earth existed. When those stars ran out of fuel, they exploded in supernovas, scattering their atoms across space. Those atoms drifted through the galaxy, gathered together by gravity, and eventually became the sun, the Earth, and you. You are made of stardust. You're the universe looking at itself, wondering about itself, finding peace in itself. Fact 26. The farther out into space we look, the farther back in time we see. This happens because light takes time to travel, and the universe is so incredibly large that light from distant objects takes millions or even billions of years to reach us. When astronomers point their telescopes at galaxies that are billions of light years away, They're seeing those galaxies as they were billions of years ago, when the universe was much younger. It's like looking through a window into the past. We can watch the story of the universe unfold just by looking deeper into space. The most distant things we can see are showing us what the universe looked like when it was just a baby, still forming its first stars and galaxies. Fact 27. There are waves in space called gravitational waves. When really massive objects like black holes or neutron stars orbit each other and eventually crash together, they create ripples in the fabric of space itself. These ripples spread out in all directions at the speed of light, stretching and squeezing space as they pass through. Scientists detected gravitational waves for the first time in 2015, proving that space isn't just empty background, but something that can bend and wave and carry information. These waves have travelled across the universe to reach us, bringing news of violent cosmic events that happened millions or billions of years ago. Fact 28. Time moves slower in stronger gravity. If you stood at the bottom of a mountain and your friend stood at the top, time would pass slightly faster for your friend than for you, because gravity is a little bit weaker up there. The difference is tiny, far too small to notice in daily life, but it's real and measurable with atomic clocks. This means that your head is actually aging faster than your feet, by about 90 billionths of a second over the course of your entire life. Gravity doesn't just pull on objects, it pulls on time itself. Fact 29. There's a spot in space called the Great Attractor, and it's pulling our galaxy toward it. The Milky Way, along with thousands of other galaxies, is moving in the direction of this mysterious region. Scientists aren't entirely sure what the Great Attractor is. It might be an enormous concentration of mass, perhaps a supercluster of galaxies hidden behind the dust and stars of our own galaxy. We're moving toward it at about 1,000,000 miles per hour, but because space is so vast, we won't get there for billions of years. The universe is full of invisible hands, pulling and pushing everything into a slow cosmic dance. Fact 30. If you could fold a piece of paper in half 50 times, it would be thick enough to reach the sun. Of course, you can't actually fold a piece of paper that many times because it becomes too thick and stiff after just a few folds. But this thought experiment shows you how quickly exponential growth works. Each fold doubles the thickness, and by the time you reach 50 folds, the paper would be about 100 million kilometers thick. This is the same kind of mathematics that describes how the universe expanded in its earliest moments, growing from something smaller than an atom to something enormous in a fraction of a second. Fact 31. Neutron stars are the collapsed cores of massive stars that exploded in supernovas. They're incredibly dense, packed so tightly that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. A neutron star is like taking all the mass of our sun and crushing it down into a sphere only about 20 kilometers across. Some neutron stars spin hundreds of times per second, sending out beams of radiation like cosmic lighthouses. When those beams sweep past Earth, we detect them as pulses, and we call these objects pulsars. They keep time more accurately than any clock we've ever built. Fact 32. The concept of now is different depending on where you are in the universe. Because of the way space and time are connected, two events that seem to happen at the same time, from one perspective might happen at different times from another perspective. If you're standing still and someone else is moving very fast relative to you, you might disagree about whether two distant events happen simultaneously or one after the other. There's no universal now that everyone agrees on. Time is more like a landscape that looks different depending on where you're standing and how fast you're moving. Fact 33. The universe has a temperature. Right now, the average temperature of space is about 2.7 degrees above absolute zero. Absolute zero is the coldest possible temperature, the point where atoms stop moving entirely. The universe started out incredibly hot, trillions of degrees in the first moments after the Big Bang, but as space expanded, it cooled down. In the far future, billions and billions of years from now, the universe will be even colder as it continues to expand and the stars burn out one by one. Eventually, it might reach a state where everything is dark and frozen, unless something we don't understand yet changes the story. Fact 34. Light can be bent by gravity. When light from a distant star passes close to a massive object like another star or a galaxy, the gravity of that object curves the path of the light, like a lens. This effect is called gravitational lensing, and astronomers use it to study objects that are too far away or too faint to see directly. Sometimes gravity can create multiple images of the same object, or stretch it into arcs and rings across the sky. It's a beautiful reminder that space itself can be shaped and curved, and that light follows the curves like a river following the contours of the land. Fact 35. There are more than 100 billion galaxies in the observable universe, and each one contains millions or billions or even trillions of stars. Each galaxy is its own island city of stars, separated from other galaxies by vast distances of mostly empty space. Some galaxies are spiral-shaped like the Milky Way, some are elliptical, shaped like footballs or spheres. Some are irregular, with no clear shape at all, twisted and torn by collisions with other galaxies. And in almost every direction we look, no matter how empty a patch of sky appears, if we look long enough and carefully enough, we find more galaxies, more stars, more worlds. Fact 36. If you fell into a black hole, something called spaghettification would happen to you. The gravity at your feet would be so much stronger than the gravity at your head that you would be stretched out like a piece of spaghetti. Your body would be pulled longer and thinner until eventually you were torn apart at the atomic level. This would happen before you even reach the event horizon, the point of no return around a black hole. It's one of the most violent ends imaginable, but also one of the most strange, because from your perspective time would be doing impossible things, and from the perspective of someone watching you would appear frozen forever. Fact 37. The planets in our solar system all orbit the Sun in roughly the same flat plane, like marbles rolling around the rim of a plate. This happened because the solar system formed from a spinning disk of gas and dust about 4.6 billion years ago. As the disk spun, gravity pulled material together in the center to form the Sun, and the leftover material in the disk clumped together to form the planets. The spinning motion of that original disk is still preserved in the orbits of the planets today. Everything in the solar system is still moving in the pattern that was set billions of years ago, like a song that's been playing since before anything on Earth was alive. Fact 38. Time and space together make something called space-time. They're not separate things. They're woven together into a single fabric that makes up the universe. When you move through space, you're also moving through time. When gravity pulls on you, it's actually bending space-time around you. This idea comes from the work of a scientist named Albert Einstein, who showed that what we experience as gravity is really just the curves and dips in space-time caused by massive objects. A planet orbits a star not because the star is pulling on it with an invisible force, but because the star curves space-time and the planet is following the natural curve, like a ball rolling along the slope of a hill. Fact 39. There are clouds in space called nebulas, and they're the places where stars are born. A nebula is a giant cloud of gas and dust, sometimes hundreds of light years across. Over millions of years, parts of the cloud collapse under their own gravity, getting denser and hotter until nuclear fusion begins in the center and a new star lights up. The leftover gas and dust often form planets around the star. Our Sun was born in a nebula like this, along with probably hundreds or thousands of other stars that have since drifted away across the galaxy. Every star you see was born from a cloud, and when stars die, they return their material to space, creating new clouds where future stars will be born. Fact 40. The speed of light isn't just about light. It's the speed limit of the universe, the fastest that anything can possibly go. Not just light, but also information, cause and effect, any kind of influence from one place to another. Nothing can travel faster than light, and this creates a kind of horizon around us. We can only see and know about the parts of the universe where light has had time to reach us since the Big Bang. There might be parts of the universe that are so far away that their light will never reach us because space is expanding too fast. Those parts are beyond our horizon, forever unknowable, entire regions of reality that we can never see or visit or touch. Fact 41. The Earth's rotation is gradually slowing down. Each day is getting longer, but only by about 1.7 milliseconds per century. This happens because of the friction created by tides, which are caused by the Moon's gravity. The energy from Earth's rotation is slowly being transferred to the Moon, which is why the Moon is gradually moving away from us. Hundreds of millions of years ago, days were much shorter, and the Moon was much closer. Dinosaurs experienced days that were only about 23 hours long. In the far future, if Earth and the Moon are still around, days will be even longer, and the Moon will be farther away, perhaps so far that it will appear smaller in the sky. Fact 42. Dark matter is one of the greatest mysteries in science. We can't see it, we can't touch it, and we don't know what it's made of. But we know it's there because of the way it affects things we can see. Galaxies spin faster than they should based on the visible matter they contain. Clusters of galaxies are held together by more gravity than the stars and gas can account for. Something invisible is out there, making up about 85% of all the matter in the universe. Scientists call it dark matter because it doesn't emit or absorb light. It's like a ghost that we can only detect by watching how it moves the things around it. Fact 43. When stars die, they do it in different ways depending on how massive they are. Small stars like our Sun will eventually swell up into red giants, shedding their outer layers and leaving behind a hot, dense core called a white dwarf. Medium-sized stars might explode gently, creating beautiful clouds of glowing gas called planetary nebulas. Really massive stars go out in spectacular supernova explosions, outshining entire galaxies for a few weeks or months, and the most massive stars of all collapse into black holes, where their matter is crushed out of existence and all that remains is gravity so strong that nothing can escape. Every star has its own story, its own life and death. Fact 44. Space and time began together, but they might not end together. Some scientists think the universe will keep expanding forever, with galaxies moving farther and farther apart until the stars all burn out and everything becomes cold and dark. Others think expansion might eventually stop and reverse, causing everything to collapse back together in a big crunch, the opposite of the Big Bang. Still others propose that the universe might tear itself apart in a big rip, where space expands so fast that it breaks apart galaxies, then stars, then planets, then atoms. We don't know how the story ends yet. We're living in the middle chapters, looking forward and backward, trying to read the clues. Fact 45. The light from the sun takes about 8 minutes and 20 seconds to reach Earth. This means that when you look at the sun, you're seeing it as it was 8 minutes ago. If the sun suddenly disappeared, we wouldn't know it for 8 minutes. We would still see it shining in the sky, still feel its warmth, because those last photons of light would still be travelling through space toward us. And then, 8 minutes after the sun vanished, darkness would arrive all at once, travelling at the speed of light, spreading across the Earth like a wave. The night would come not because the sun set, but because the sun ceased to be. Fact 46. There's something called the cosmic web, a structure that stretches across the entire universe. Galaxies aren't scattered randomly through space. They're arranged in long filaments and sheets, like a three-dimensional spider web, with huge empty voids in between. The filaments are made of dark matter and regular matter, drawn together by gravity over billions of years. Where the filaments intersect, you find massive clusters of galaxies. If you could zoom out and see the whole universe at once, it would look like foam or a sponge, with structure on every scale. This pattern formed from tiny variations in density in the very early universe, blown up by expansion and shaped by gravity. Fact 47. Time dilation isn't just a strange fact about the universe. It's something we have to account for in everyday technology. The satellites that run navigation systems are moving fast and are farther from Earth's gravity than we are, so time runs differently for them than it does for us on the ground. If we didn't correct for these differences, navigation systems would become less accurate by kilometers each day. Every time you use a phone or a car to find your way somewhere, you're relying on calculations that take into account the way time bends and stretches. The strangeness of space-time is woven into the tools we use without even thinking about it. Fact 48. There are binary star systems where two stars orbit around each other, bound together by gravity. Sometimes these stars are very different from each other, one large and one small, one hot and one cool. Sometimes they're almost identical twins dancing around their common centre of mass. If you stood on a planet in a binary star system, you might see two suns in the sky, rising and setting at different times, casting double shadows. More than half of all stars in the galaxy are part of binary or multiple star systems. Our Sun is actually unusual for being alone. Most stars have companions, partners in their long journey through space and time. Fact 49. The idea of absolute time, time that flows the same for everyone everywhere, turned out to be wrong. Before Einstein's work, people thought time was like a river that carried everything along at the same rate. But experiments and observations showed that time is flexible, different for different observers, depending on how fast they're moving and how strong the gravity is around them. This was shocking when it was first discovered. It seemed to violate common sense. But it's been tested thousands of times and it's always proven true. Our intuition about time, built from our everyday experience, is just an approximation that works well at low speeds and weak gravity. The deeper truth is stranger and more beautiful. Fact 50. When galaxies collide, the stars almost never actually hit each other. Galaxies are mostly empty space. Even though a galaxy contains billions or hundreds of billions of stars, those stars are separated by such vast distances that when two galaxies pass through each other, the stars slip past like raindrops passing through a cloud. But the galaxies are still transformed by the collision. Gravity pulls streams of stars out into long tails. Gas clouds crash together, triggering waves of new star formation. The shapes of the galaxies are distorted and blended. Eventually, the two galaxies merge into one larger galaxy. Our Milky Way is on a collision course with the Andromeda Galaxy. And in about 4 billion years, they'll meet and dance and become something new together. Fact 51. The universe has no center and no edge, at least not in the way we usually think about those things. When the Big Bang happened, it didn't explode into empty space from a single point. Instead, space itself began expanding everywhere at once. Every point in the universe was the starting point. This means that from any galaxy's perspective, it looks like all the other galaxies are moving away from it, as if it were the center. But every galaxy sees the same thing. There's no special location, no middle of everything. The universe is like the surface of a balloon being inflated, where every point on the surface is equivalent to every other point, and there's no center on the surface itself. If you could somehow step outside the universe and look at it from beyond, you might see something with a center, but from within, from our perspective, every location is just as valid as every other. We're not at the edge, and we're not in the middle. We're simply here, one point among infinite points, all equally distant from the beginning. Fact 52. Some particles in the universe can be in two places at once, or at least they behave that way until we measure them. This is part of quantum mechanics, the rules that govern the smallest scales of reality. An electron, for example, doesn't have a definite position until something interacts with it or measures it. Before that, it exists in a state of possibility spread out across space. This seems impossible, and it clashes with our everyday experience where things are always in one place at one time. But experiments have proven it over and over. The universe at its smallest scales is far stranger than the universe we see around us, and nobody fully understands why. Scientists have done experiments where they send individual particles through two slits at once, and the particles create interference patterns as if they went through both slits simultaneously. The moment you try to observe which slit the particle actually went through, the pattern changes, as if the particle knew it was being watched. Reality at the quantum level doesn't follow the rules we learned from living in the everyday world. It's as if the universe keeps its deepest workings hidden until we look away. Fact 53. There are moons in our solar system that might have oceans beneath their surfaces. Europa, which orbits Jupiter, is covered in ice. But beneath that ice there might be a liquid water ocean kept warm by tidal forces from Jupiter's gravity. The surface of Europa is crisscrossed with cracks and ridges, suggesting that the ice floats on water below and is constantly being broken and reformed. Enceladus, a small moon of Saturn, shoots geysers of water ice into space from cracks in its surface, suggesting an ocean below. Scientists have detected organic molecules in those geysers, the building blocks of life. These hidden oceans could be some of the best places in the solar system to look for life beyond Earth. Life as we know it needs liquid water, and these moons have it, along with energy and organic chemicals. Beneath the ice, in total darkness, there might be life forms we can't even imagine yet. Perhaps there are creatures swimming in those alien seas, never seeing sunlight, never knowing that a universe of stars exists above the ice. They would live in perpetual night, in cold water warmed only by the flexing of their world as it orbits its giant planet. It's a humbling thought that life might be hidden in places we once thought were barren and dead. Fact 54. Time is affected by motion in ways that seem backwards to our intuition. If you're on a spaceship traveling very fast and you look back at Earth, you would see time moving slower there. But someone on Earth looking at you would see your time moving slower. Both perspectives are correct within their own reference frames. This isn't a contradiction. It's just how space-time works. Time isn't a single universal thing that everyone experiences the same way. It's personal and depends on your path through space-time. Only when you come back together and compare clocks directly do you find out who aged more and who aged less. The person who travelled faster or spent time in stronger gravity will have aged less. This has been tested with atomic clocks on airplanes and satellites. The clocks that flew came back showing slightly less time had passed compared to clocks that stayed on the ground. The difference is tiny, measured in billionths of a second, but it's real and measurable. Time truly does bend and stretch depending on how you move through the universe. It's not just an illusion or a trick of perception. It's built into the foundation of reality itself. Fact 55. The Voyager spacecraft, launched in the 1970s, are now in interstellar space, beyond the influence of the sun's solar wind. They're the most distant human-made objects, over 14 billion miles away and still travelling. They carry golden records with sounds and images from Earth, messages to any civilization that might find them millions of years from now. The records contain greetings in dozens of languages, music from different cultures, sounds of nature like wind and birds and whales, and images showing what life on Earth is like. The Voyagers are moving at about 38,000 miles per hour, but even at that speed, it would take them tens of thousands of years to reach another star system. They're lonely ambassadors from humanity, drifting through the dark, carrying our greetings into the infinite future. Long after everyone who built them is gone, long after the civilizations that launched them have changed beyond recognition, the Voyagers will still be out there, silent and cold, waiting for someone to find them. Their time capsules and messages in bottles thrown into an ocean so vast that they may never be found. But they represent something beautiful about humanity, the desire to reach out, to say hello to the universe, to leave some trace that we were here. Fact 56. There's a difference between the observable universe and the whole universe. The observable universe is the part we can see, the part where light has had enough time to reach us since the Big Bang. It's about 93 billion light-years across, but the whole universe is probably much, much bigger than that, possibly infinite. There could be regions so far away that we'll never see them because space between us and them is expanding faster than light can travel through it. There might be countless galaxies and stars and worlds that are forever beyond our reach, existing in a part of reality we can never access or even prove is there. These distant regions might have their own galaxies, their own stars, their own planets where life has emerged and built civilizations and wondered about the universe just like we do. But we'll never meet them, never communicate with them, never even know they exist. The expansion of space creates a horizon, and beyond that horizon is mystery. It's like living on an island and knowing that there are other islands out there. But the ocean between you is growing wider every moment, and eventually it will be so wide that no ship could ever cross it. We're isolated not by distance alone, but by the very fabric of space-time itself. Fact 57. Red dwarfs are the most common type of star in the universe. They're small, dim, and burn their fuel very slowly. A red dwarf can live for trillions of years, far longer than the current age of the universe. Our sun will die in about 5 billion years, but red dwarfs that exist today will still be shining long after the sun is gone, long after most other stars have burned out. In the far future, red dwarfs will be the last stars left, glowing faintly in an otherwise dark universe. They're patient stars, witnesses to the long arc of cosmic time outlasting everything else. Many red dwarfs have planets orbiting them, and some of those planets might be in the habitable zone where liquid water can exist. Because red dwarfs live so long, any life that evolves on their planets would have trillions of years to develop and change and spread. By the time a red dwarf finally dies, life on its planets could have transformed into something we can't even begin to imagine. These small, humble stars might be the cradles of the longest-lasting civilizations in the universe, communities that have billions of times more history than humanity will ever have. Fact 58. Space isn't perfectly flat. On large scales, the universe has geometry, and that geometry is determined by how much matter and energy it contains. If there's enough matter, space could curve back on itself like the surface of a sphere, making the universe finite but with no edge. If there's too little matter, space could curve the opposite way, like a saddle, and extend infinitely. Current measurements suggest the universe is very close to flat, which means parallel lines stay parallel forever, and space extends infinitely in all directions. But we're still measuring, still looking, trying to understand the true shape of everything. The geometry of space determines the ultimate fate of the universe and affects how light travels across cosmic distances. A curved universe would eventually bring light back to where it started, like travelling around the Earth and returning to your starting point. A flat or saddle-shaped universe would let light travel forever, never returning. These aren't just abstract mathematical concepts. They have real consequences for what we can see and where we can go. The shape of space is the shape of possibility itself. Fact 59. When you look at a rainbow, you're seeing light that has been split by water droplets in the air. Each colour of light bends by a slightly different amount when it passes through water, so white sunlight gets separated into red, orange, yellow, green, blue, and violet. But this same principle works everywhere in the universe. When astronomers look at the light from distant stars and galaxies, they can split that light into its component colours and see dark lines or bright lines at specific wavelengths. These lines tell us what elements are present in those distant objects, how fast they're moving, and how far away they are. We can read the composition and motion of stars that are billions of light years away just by studying their light. Each element produces its own unique pattern of lines, like a fingerprint. Hydrogen has its pattern, helium has another, oxygen and carbon and iron each have their own. By matching these patterns, astronomers can determine what stars are made of without ever going there. They can also tell if a star is moving toward us or away from us, because the motion shifts the wavelengths of light, making them slightly bluer if the star is approaching or redder if it's receding. This technique, called spectroscopy, has revealed more about the universe than almost any other tool. It's turned starlight into stories, distant suns into open books. Fact 60. The Earth moves through space in multiple ways at the same time. It spins on its axis once every 24 hours, giving us day and night. It orbits the Sun once every 365 days, giving us the year and the seasons. The Sun orbits the centre of the Milky Way galaxy once every 225 to 250 million years, carrying all its planets along with it, and the Milky Way itself is moving through space toward the Andromeda galaxy and being pulled by the Great Attractor. All these motions are happening simultaneously, layered on top of each other. We're not sitting still in space. We're racing through it in spirals and curves, following the gravity of objects near and far, tracing paths that won't repeat for millions or billions of years. If you could somehow mark your position in space and return to that exact spot, you would never actually come back to the same place, because the Earth, the Sun, and the galaxy have all moved on. There's no fixed reference point in the universe, no cosmic landmark that stays still. Everything is in motion, always has been, always will be. We're all travellers on a journey that began before we were born and will continue long after we're gone. Fact 61. There's something called Hawking radiation, named after the physicist Stephen Hawking who predicted it. Even black holes aren't completely black. At the edge of a black hole's event horizon, pairs of particles can form from the energy of empty space. Usually these particle pairs annihilate each other instantly, but at the event horizon, one particle can fall into the black hole while the other escapes. From far away, it looks like the black hole is emitting radiation and losing mass. Over incredibly long periods of time, far longer than the current age of the universe, black holes can actually evaporate completely. Even these giants of gravity are not eternal. A small black hole might evaporate in about 10 to the power of 67 years. A supermassive black hole like the ones at the centres of galaxies might take 10 to the power of 100 years. These timescales are so long that they're almost meaningless, but the principle remains. Nothing lasts forever. Even black holes, which seem like the ultimate end state of matter, will eventually give their energy back to the universe and disappear. The final black hole will evaporate in an empty, cold, dark universe, releasing one last burst of radiation into the void, and then there will be nothing left but photons spreading farther and farther apart forever. Fact 62. The planets in our solar system formed from the leftovers of the Sun's birth. After the Sun ignited at the centre of the spinning disk of gas and dust, the remaining material began to stick together. Tiny grains collided and merged, forming pebbles, then rocks, then boulders. These grew into planetesimals, objects the size of mountains or moons. The planetesimals crashed together and either merged into larger bodies or were broken apart by the collisions. Eventually, after millions of years of chaos and violence, the planets reached roughly their current sizes and settled into stable orbits. The process was messy and unpredictable, full of accidents and lucky breaks that determined which worlds would be rocky and which would be giant balls of gas. Earth might have been struck by a Mars-sized object early in its history, and that collision threw debris into orbit that eventually became the Moon. Venus and Earth started out similar, but Venus ended up too close to the Sun and became a hellish world with surface temperatures hot enough to melt lead. Mars started with water, and maybe even life, but it lost its atmosphere and became a frozen desert. These outcomes weren't planned or predetermined. They were the result of countless small events, collisions and near misses, gravitational nudges and orbital resonances. The solar system we see today is just one possible outcome from many that could have happened. Fact 63. Time moves at different rates depending on temperature, in a way that's related to entropy and the arrow of time. Hot things have more energy and their atoms move faster, exploring more possible states. Cold things move slower, with fewer possibilities. At absolute zero, motion stops entirely. The direction of time, the fact that we remember the past but not the future, is connected to the increase of entropy, the tendency of systems to become more disordered over time. A broken cup doesn't spontaneously reassemble itself because the disordered state is vastly more probable than the ordered state. Time's arrow points in the direction of increasing disorder, from order to chaos, from structure to randomness. In the early universe, everything was very ordered, concentrated in a tiny space with very low entropy. As the universe expanded, entropy increased. Stars formed and burned and died, scattering their atoms. Galaxies clustered and spread apart. Energy dispersed from hot regions to cold regions. This progression from low entropy to high entropy is what gives time its direction. If somehow the universe started contracting instead of expanding, if entropy started decreasing, would time run backward? Would causes follow effects instead of preceding them? These are questions without clear answers, puzzles that sit at the intersection of physics and philosophy. Fact 64. There are storms on Jupiter that have been raging for hundreds of years. The Great Red Spot is a hurricane-like storm larger than Earth, with winds over 400 miles per hour. It's been observed since at least the 1600s, and it might be much older than that. Unlike storms on Earth, which are powered by heat from the sun and die out when they move over land or cold water, Jupiter's storms are driven by the planet's own internal heat and have nothing to stop them. They can last for centuries or longer. Jupiter's atmosphere is a place of endless motion, bands of clouds racing around the planet, storms within storms, chaos that never settles. The Great Red Spot has been shrinking over the past century, and nobody knows if it will eventually disappear or if it will stabilize at a smaller size. Other storms come and go, merging with each other or being torn apart by the planet's fierce winds. Jupiter is a world without a solid surface, just layers of gas getting denser and hotter as you go deeper, until eventually the pressure is so intense that hydrogen becomes metallic and conducts electricity. The storms we see are just the surface manifestation of convection currents that might extend thousands of miles down into the planet's interior. It's a reminder that planets can be wildly different from Earth, with weather systems that would dwarf anything we experience here. Fact 65. The cosmic microwave background is almost perfectly uniform in all directions, but not quite. There are tiny variations in temperature, differences of only a few millionths of a degree. These variations are the seeds of all the structure we see in the universe today. Slightly denser regions had a bit more gravity, which pulled in more matter, which increased the gravity further. Over billions of years, these tiny ripples grew into galaxies and galaxy clusters in the cosmic web. Everything we see, every star and planet and living thing grew from imperfections in the smooth glow of the early universe. Without those tiny differences, everything would have stayed smooth and empty forever. The universe would have been a thin, uniform gas spreading outward forever, never forming stars or galaxies or anything interesting. But those small quantum fluctuations in the first moments after the Big Bang were amplified by inflation, a period of incredibly rapid expansion. They were stretched from microscopic scales to cosmic scales, becoming the patterns we see in the microwave background. When scientists study those patterns, they're looking at the baby picture of the universe, seeing the earlier structures that would eventually become everything we know. It's humbling to realize that the galaxies, the stars, the planets, and ultimately life itself all trace back to random quantum jitters in the first fraction of a second after time began. Fact 66. There's a theoretical concept called a white hole, which is the opposite of a black hole. While nothing can escape from a black hole once it crosses the event horizon, nothing can enter a white hole. Matter and light would be ejected from it continuously. White holes would be incredibly unstable, and probably don't exist in nature, but they're mathematically possible solutions to the equations that describe space-time. Some scientists have speculated that the Big Bang might have been a kind of white hole, a moment when space and time and matter burst outward from a single point. But this is still just speculation, an idea without proof, a dream of mathematics. The equations of general relativity are time-symmetric, meaning they work equally well running forward or backward in time. A black hole running backward in time would look like a white hole, but in the real universe, time has a direction, and processes that work one way don't work the other way. A cup falls and breaks, but broken pieces don't spontaneously leap up and form a cup. Similarly, matter falls into black holes, but we never see matter spontaneously ejected from white holes. The mathematics allows for possibilities that nature doesn't seem to use. Fact 67. The stars you see at night aren't randomly scattered. Many of them are part of constellations, patterns that humans have recognized for thousands of years. But those patterns are accidents of perspective. The stars in a constellation aren't near each other in space. Some might be only a few dozen light years away, while others are hundreds or thousands of light years distant. They just happen to lie in roughly the same direction from our point of view. If you travelled to another star system and looked back, the constellations would be completely different. The patterns would dissolve and new patterns would form. The sky's familiar shapes are specific to Earth, to this moment in time, to our small corner of the galaxy. Ancient people looked at these patterns and saw heroes and animals and instruments. They told stories about them, used them for navigation, marked the seasons by their rising and setting. These stories were passed down through generations, becoming part of human culture and mythology. But the stars themselves know nothing of our stories. They're just distant suns, burning in the dark, unaware that beings on a small planet are looking up at them and finding meaning in their arrangement. Fact 68. Dark energy is even more mysterious than dark matter. While dark matter pulls things together with gravity, dark energy seems to be pushing things apart, causing the expansion of the universe to accelerate. About 68% of the universe is dark energy, but we have no idea what it is. It could be a property of space itself, a kind of energy that exists everywhere equally. It could be a new force or field that we haven't discovered yet. Whatever it is, it's winning. The universe is expanding faster and faster, and if this continues, eventually galaxies will be so far apart that beings in one galaxy won't be able to see any others. The night sky will be empty except for the stars in their own galaxy. Civilizations that arise billions of years from now will look up and see only their own stars. They won't know that other galaxies exist unless they find records or evidence left by earlier civilizations. They'll think their galaxy is the entire universe. This is sometimes called the Big Freeze or heat death. A future where the universe becomes cold, dark and empty, with isolated islands of stars separated by ever-growing voids of nothingness. It's a lonely vision of the far future, but it's based on our best current understanding of how the universe works. Fact 69. Saturn's rings are made of billions of pieces of ice and rock, ranging in size from tiny grains to house-sized boulders. They orbit the planet in a flat disk, held in place by gravity and shaped by the pull of Saturn's moons. The rings are probably the remains of a moon or comet that came too close to Saturn and was torn apart by tidal forces. They're beautiful and delicate, structures of incredible complexity organised by gravity into thousands of narrow ringlets. But they won't last forever. Material from the rings is slowly falling into Saturn's atmosphere, raining down on the planet like cosmic snow. In 100 million years or so, the rings might be much thinner or gone entirely. We're lucky to live in a time when we can see them in their full glory. Future generations, if they exist, might look at images of Saturn's rings the way we look at pictures of glaciers that have melted or forests that have been cut down, remnants of beauty that once was but is no longer. The rings remind us that even the grandest structures in the universe are temporary, that everything is in flux, that nothing stays the same forever. Beauty and transience are intertwined, and perhaps that's what makes beauty so precious. Fact 70. If you could travel faster than light, which is impossible as far as we know, you could theoretically travel backward in time. The mathematics of relativity allow for this, creating what are called closed, time-like curves. But these solutions come with paradoxes. What happens if you go back in time and prevent your past self from ever starting the journey? These questions suggest that faster-than-light travel probably can't happen, not because we lack the technology, but because it would break causality, the principle that causes come before effects. The universe seems to have built-in protections against time paradoxes, speed limits that keep the past safe from the future. Some scientists have proposed that while you might be able to travel to the past, you couldn't change it in any way that would create a paradox. Others suggest that any attempt to create a paradox would cause the timeline to split into parallel universes, so you wouldn't actually be changing your own past, but creating a new branch of reality. These ideas venture into the realm of speculation, far beyond what we can currently test or observe, but they show how seriously physicists take the problem of time travel and the paradoxes it creates. The universe has rules, and those rules seem designed to prevent certain kinds of chaos. Fact 71. The sun is slowly getting brighter. Over the billions of years it's been burning, it has increased in brightness by about 30%. This happens because as the sun fuses hydrogen into helium, the helium accumulates in the core, making it denser and hotter, which causes the fusion rate to increase. In another billion years or so, it will be hot enough that Earth's oceans will begin to evaporate. The water vapour will trap even more heat, creating a runaway greenhouse effect. Eventually, Earth will become too hot for life as we know it, long before the sun swells into a red giant. This isn't something to worry about in any personal sense. A billion years is an almost incomprehensible amount of time. Humanity might not even exist anymore. We might have evolved into something different, or spread to other worlds, or gone extinct. But it's a reminder that nothing lasts forever. Not even our world, not even our sun. The Earth has been a home for life for about 3.5 billion years, but it won't be habitable forever. The window of time when conditions are just right for life is finite. We're living in the middle of that window, in what might be the golden age of Earth's habitability. Before us, the Earth was too violent, too unstable. After us, it will be too hot, too harsh. We exist in a brief moment of cosmic grace. Fact 72. There are magnetic fields throughout the universe. The Earth has one, generated by currents in its molten iron core. The Sun has one, twisted into complex shapes by its rotation and convection. Even galaxies have magnetic fields, threading through the space between stars, organized by the motions of charged particles and plasma. These fields guide the motion of charged particles, creating beautiful shapes like the loops and arcs above the Sun's surface and the auroras that dance near Earth's poles. They protect planets like Earth from harmful radiation, deflecting the solar wind and cosmic rays that would otherwise strip away the atmosphere and bombard the surface. They channel energy and matter across vast distances, shaping nebulas and guiding the formation of stars. Magnetism is one of the fundamental forces woven into the fabric of reality, invisible but powerful, shaping the universe in ways we're only beginning to understand. When you use a compass to find north, you're tapping into Earth's magnetic field, a force that extends thousands of miles into space and has been guiding travellers for thousands of years. That same kind of force exists on scales unimaginably larger, organising matter and energy across entire galaxies. Fact 73. The universe is full of leftovers from its own history. When the Big Bang happened, it created mostly hydrogen and helium, with tiny amounts of lithium. Every other element, every atom of carbon and oxygen and iron and gold, was created later inside stars or in supernova explosions. When you breathe, you're breathing atoms that were forged in stars. When you touch something, the atoms in your hand and the atoms in that object were created billions of years ago in nuclear fires. We're not just living in the universe, we're made of the universe's history. Every element tells a story of where it came from, how it was made, what star it was born in. Carbon, which forms the basis of all life on Earth, is made in the cores of aging stars. Oxygen comes from massive stars that explode as supernovas. Iron is made in the final moments before a supernova, in the last seconds of a star's life when the core collapses. Gold and other heavy elements are created when neutron stars collide, in cataclysms so violent that they send ripples through space-time itself. The atoms in your body have travelled across the galaxy, drifted through nebulas, been part of multiple generations of stars. They're older than the Earth, older than the Sun, witnesses to billions of years of cosmic history. In a very real sense, you are stardust, and so is everything around you. Fact 74. Time might be infinite in both directions, or it might have a beginning and an end. We know the universe had a beginning about 13.8 billion years ago, but we don't know if time itself began then, or if something existed before. Maybe the Big Bang was a transition from a previous state rather than the absolute start of everything. Some theories suggest the universe goes through cycles, expanding and contracting repeatedly, with each Big Bang followed eventually by a big crunch that leads to a new Big Bang. Others propose that our universe is just one bubble in an eternal multiverse where new universes are constantly forming and evolving. And in the future, time might go on forever, or it might end if the universe undergoes some kind of final collapse or transformation. These questions sit at the edge of what science can currently answer. They're places where physics meets philosophy, where mathematics meets mystery, where knowledge gives way to wonder. We can describe what happened a fraction of a second after the Big Bang, but we can't yet say what caused it, or what, if anything, came before. We can predict the far future of the universe based on current expansion rates, but we can't be certain that the rules won't change. Time itself might be something that emerges from a deeper level of reality, something that began and might end rather than an eternal backdrop against which events unfold. Fact 75. Comets are sometimes called dirty snowballs because they're made of ice mixed with dust and rock. They spend most of their time in the cold outer reaches of the solar system, in regions like the Kuiper Belt or the Oort cloud, which extends halfway to the nearest star. But occasionally their orbits bring them close to the Sun. When that happens, the Sun's heat causes the ice to vaporize, creating a glowing cloud called a coma around the comet's nucleus, and sometimes a long tail that points away from the Sun, pushed by the solar wind and radiation pressure. People have been watching comets for thousands of years, often seeing them as omens or messages, signs of change or disaster. But they're just travellers, ancient objects left over from the solar system's formation, carrying ice and organic molecules that might have helped seed life on Earth billions of years ago. When comets crashed into the young Earth, they brought water and complex carbon compounds. Some scientists think that the oceans and maybe even the first building blocks of life came from comets. These icy wanderers, now relegated to the dark edges of the solar system, might have been the delivery system that made our world habitable. They're time capsules too, preserving material from the birth of the solar system in their frozen interiors. By studying comets, we can learn what conditions were like 4.5 billion years ago, when the sun and planets were still forming. Fact 76. There are places in the universe where time moves so slowly it almost stops. Near the event horizon of a black hole, gravity is so intense that time stretches like taffy being pulled. If you watch someone fall toward a black hole from a safe distance, you would see them move slower and slower as they approached the edge. They would appear to freeze, stuck in time, never quite crossing over. Their image would become redder and dimmer as the light from them struggled to escape the black hole's gravity. But from their perspective, time would feel normal. They would fall through the event horizon in moments, unaware that from the outside universe they appeared frozen forever. This isn't just theory or imagination. It's what the mathematics of space-time predicts, and we've observed similar effects on smaller scales with satellites and atomic clocks. Time is not a river that flows the same for everyone. It's more like an ocean with currents and eddies, places where it rushes forward and places where it barely moves at all. Near massive objects, time slows down. Far from gravity, time speeds up. The universe is full of these temporal gradients, invisible but real, shaping the experience of every particle and every being. If you could somehow watch the entire universe from a position outside time, you would see different regions aging at different rates, some racing forward, while others crawled along, all following the curves and valleys of space-time created by matter and energy. Fact 77. Mars once had rivers and lakes, and possibly even an ocean covering much of its northern hemisphere. We know this because spacecraft orbiting Mars have photographed ancient riverbeds, deltas where rivers once emptied into larger bodies of water, and shorelines marking the edges of vanished seas. Some of these features are billions of years old, carved when Mars was young, and the solar system was still settling into its current configuration. Billions of years ago, Mars had a thicker atmosphere and a warmer climate. Water flowed on its surface, carving valleys and depositing sediments in layers we can still see today. There might have been rain falling from Martian skies, filling lakes and streams, creating an environment that could have supported life. But Mars is smaller than Earth and has weaker gravity, and over time it lost most of its atmosphere to space. The solar wind, a stream of charged particles from the sun, gradually stripped away the protective blanket of air. Without that protection, the water evaporated or froze, the rivers dried up, the lakes turned to ice, and the planet became the cold desert we see today. But beneath the surface there might still be liquid water, trapped in underground reservoirs or briny lakes beneath the polar ice caps. There might even be microbial life still clinging to existence in those hidden places, organisms that survived the transformation of Mars from a wet world to a dry one, adapting to life underground where water still exists. If we find life on Mars, even simple bacteria, it would answer one of humanity's oldest questions: are we alone, or is life common in the universe? Mars might hold that answer, buried beneath its rust-coloured surface, waiting to be discovered. Fact 78. Light can be thought of as both a wave and a particle, depending on how you observe it. This is called wave-particle duality, and it's one of the strange truths at the heart of quantum mechanics. When light travels through space, it behaves like a wave, with peaks and troughs that can interfere with each other, creating patterns of brightness and darkness. But when light interacts with matter, when it's absorbed by an atom or emitted from one, it behaves like a stream of particles called photons. Each photon carries a specific amount of energy, and that energy depends on the colour or frequency of the light. Blue light has more energy per photon than red light. This dual nature isn't limited to light. Electrons, atoms, even molecules can behave as both particles and waves. The smaller something is, the more obvious its wave nature becomes. Scientists have done experiments where they send individual electrons through two slits in a barrier, and the electrons create an interference pattern on a screen behind the slits, as if each electron went through both slits at once as a wave. But if you try to observe which slit the electron actually went through, the interference pattern disappears, and the electron behaves like a particle going through one slit or the other. The act of measurement changes the outcome. This blurring of the line between wave and particle shows us that our everyday categories don't apply at the quantum level. Reality is stranger and more fluid than our intuition suggests. The universe doesn't fit neatly into the boxes we create for it. It resists our attempts to pin it down, remaining mysterious and surprising no matter how much we learn. Fact 79. There are asteroids in our solar system that are made almost entirely of metal. These are thought to be the exposed cores of small planets that formed early in the solar system's history and were then shattered by collisions. When a planet forms, the process of differentiation occurs. The heaviest elements like iron and nickel sink to the centre under the pull of gravity, forming a metallic core surrounded by a rocky mantle, and possibly a thin crust on the surface. But if that protoplanet is destroyed in a collision before it finishes forming, the core can survive as a metallic asteroid while the lighter, rocky material is scattered away. Some of these asteroids contain more iron, nickel, platinum and gold than humanity has ever mined from the Earth. One asteroid called Psyche, located in the main asteroid belt between Mars and Jupiter, is thought to be almost entirely metal, possibly worth more than the entire global economy if we could somehow bring it back to Earth and extract its resources. Of course, doing so would flood the market and make those metals worthless, but the idea captures the imagination and has inspired plans for future mining missions. These asteroids are windows into planetary formation, showing us what the cores of planets look like. By studying them, we can learn about the processes that built the Earth and the other rocky planets, the violent early days when collisions were common and worlds were still taking shape. The Earth has a metallic core too, iron and nickel under such pressure and temperature that it behaves in ways we can barely understand. We can't dig down to see it, but we can study asteroids like Psyche and get a glimpse of what lies beneath our feet. Fact 80. The speed at which the universe is expanding is described by something called the Hubble constant, named after the astronomer Edwin Hubble, who first discovered that the universe was expanding. But scientists have measured this constant in different ways and gotten different answers, which shouldn't happen if we truly understand the universe. This discrepancy is called the Hubble tension, and it's one of the biggest mysteries in modern cosmology. One way to measure expansion is to look at the cosmic microwave background, the afterglow of the Big Bang, and work forward through time using our understanding of physics and the composition of the universe. Another way is to measure the distances and velocities of nearby galaxies directly using standard candles, like Cepheid variables and supernovas. These two methods give results that differ by several percent, which might not sound like much, but in science, when two careful measurements disagree, it usually means something important is missing from our understanding. Maybe dark energy, the mysterious force driving the accelerated expansion, is more complicated than we thought. Maybe it's not constant but changes over time. Maybe the universe's expansion has changed in ways we haven't accounted for. Maybe there's new physics we haven't discovered yet, some force or particle or field that affects the expansion rate. The Hubble tension reminds us that for all we've learned, we're still piecing together the story of the cosmos, and some of the most important chapters might still be unwritten. The universe keeps surprising us, revealing new puzzles just when we think we're close to understanding it completely. Fact 81. There are clouds of alcohol floating in space. In a region of our galaxy called Sagittarius B2, near the center of the Milky Way, there's a cloud of gas and dust that contains ethanol, the same alcohol found in drinking beverages. The cloud is enormous, spanning thousands of light years and containing enough alcohol to fill trillions and trillions of bottles. Of course, you couldn't drink it because it's mixed with other chemicals, many of them toxic, and it's floating in the vacuum of space where there's no air to breathe and temperatures are near absolute zero. But it's a reminder that the molecules of life and chemistry are scattered throughout the cosmos. Space isn't empty and sterile. It's full of organic compounds, complex molecules built from carbon and hydrogen and oxygen and nitrogen. These molecules form in the gas between stars, in the atmospheres of dying stars that puff off their outer layers, in the icy surfaces of comets where radiation breaks apart simple molecules and they recombine into more complex forms. When planets form from the disk of gas and dust around a young star, they inherit this chemistry. The Earth didn't create organic molecules from scratch. They were delivered here by asteroids and comets during the period of heavy bombardment early in our planet's history, or they formed in the solar nebula before Earth even existed. The building blocks of life are common in the universe, which suggests that life itself might be common too, waiting to emerge wherever conditions are right. We might not be alone. We might be one example among countless others of the universe becoming alive and aware. Fact 82. Black holes can spin, and when they do, they drag space-time around with them like a spoon stirring honey. This effect is called frame dragging, or the lens-thirring effect, and it means that anything near a spinning black hole is pulled along with the rotation, unable to remain stationary relative to distant stars. The faster a black hole spins, the stronger this effect becomes. Some black holes spin so fast that they're nearly at the theoretical maximum, where the surface of the event horizon is moving at close to the speed of light. These rapidly spinning black holes were probably spun up by the matter falling into them, which carried angular momentum that got transferred to the black hole itself. When black holes like this feed on matter from a surrounding accretion disk, the disk's inner edge can get twisted and tilted by the frame dragging effect. They can also launch jets of particles and radiation from their poles, beams that shoot out at nearly light speed and can extend for thousands or millions of light years across space. These jets are some of the most energetic phenomena in the universe, visible across vast distances, powered by the conversion of the black hole's rotational energy and the gravitational potential energy of infalling matter. The spin of a black hole stores enormous amounts of energy, and in principle, an advanced civilization might be able to extract that energy for their own use through a process called the Penrose mechanism. It's a strange thought that a black hole, which seems like the ultimate destroyer, could also be a source of power, a cosmic battery waiting to be tapped by beings clever enough to figure out how. Fact 83. The Earth's axis is tilted at about 23.5 degrees relative to its orbit around the Sun. This tilt is why we have seasons, why summer and winter exist, why the days get longer and shorter throughout the year. When the northern hemisphere is tilted toward the Sun, it receives more direct sunlight and experiences summer, while the southern hemisphere is tilted away and experiences winter. 6 months later, the situation reverses. The tilt means that the Sun appears to move north and south in the sky over the course of the year, rising higher in summer and lower in winter. Without this tilt, there would be no seasons, just a steady climate that varied from the equator to the poles but never changed throughout the year. The length of day and night would be equal everywhere every day. The tilt also causes the length of day and night to change over the course of the year. Near the poles, the Sun can stay above the horizon for months during summer, creating the midnight sun, and disappear for months during winter, creating polar night. This tilt probably came from a collision early in Earth's history, about 4.5 billion years ago, when a Mars-sized object struck the planet and knocked it off its original rotation. That same collision threw debris into orbit that eventually coalesced to form the Moon. So the seasons we experience, the rhythm of summer and winter that has shaped life on Earth for billions of years, are the result of an ancient accident, a moment of violence that changed the planet forever and gave us our largest natural satellite. Fact 84. There are planets orbiting other stars that are nothing like the worlds in our solar system. Some are hot Jupiters, gas giants that orbit so close to their stars that their years last only a few days, and their atmospheres are heated to thousands of degrees, hot enough to vaporize metals. Their atmospheres are being stripped away by intense radiation and stellar winds, and some of them have massive comet-like tails of escaping gas. Some are super-Earths, rocky planets larger than Earth but smaller than Neptune, a type of planet that doesn't exist in our solar system at all. We don't know if they're like Earth with thicker crusts and stronger gravity, or if they're more like mini-Neptunes with deep atmospheres of hydrogen and helium. Some planets orbit binary stars, rising and setting under two suns like something from a dream or a science fiction story. Some are tidally locked, always showing the same face to their star, with one side in perpetual day and the other in perpetual night, creating extreme temperature gradients and possibly permanent twilight zones in between, where conditions might be just right for life. The diversity of planets is staggering and continues to surprise astronomers with each new discovery. We used to think that other solar systems would look like ours, with small rocky planets close to the star and giant gas planets farther out, all orbiting in roughly circular paths in the same plane. But that was just a failure of imagination, a natural bias from having only one example to study. The universe is more creative than we are. It's filled with worlds that challenge our expectations and expand our understanding of what's possible. Each new planet we discover teaches us something about how solar systems form and evolve, how different initial conditions and random events lead to different outcomes, how the same laws of physics can produce an almost infinite variety of results. Fact 85. The vacuum of space isn't completely empty. Even in the darkest, most isolated regions between galaxies, millions of light years from the nearest star, there are still a few atoms per cubic meter, mostly hydrogen and helium left over from the Big Bang. And even if you could remove all the atoms, sweep them away completely, space wouldn't be empty. It would still be filled with quantum fields, invisible but real, permeating every point in space-time. These fields give rise to the fundamental particles and forces that make up reality. The electromagnetic field gives us light and magnetism. The Higgs field gives particles their mass, allowing matter to exist as we know it. Other fields govern the strong and weak nuclear forces that hold atomic nuclei together and allow stars to shine. Even in a perfect vacuum, these fields are there, and they fluctuate at the quantum level, creating virtual particles that pop into existence for brief moments before disappearing again, borrowing energy from the vacuum itself and paying it back so quickly that they don't violate conservation of energy. The vacuum has energy, sometimes called vacuum energy or zero-point energy, the lowest possible energy state of space. It might be related to dark energy, the mysterious force driving the universe's accelerating expansion. The vacuum is not nothing. It's a seething quantum foam, a substrate of possibility from which reality emerges moment by moment, building the solid-seeming world from fluctuations and probabilities. Fact 86. Time passes more slowly at lower elevations because gravity is stronger there. If you lived your entire life in a basement, you would age slightly less than someone who lived on the top floor of a skyscraper. The difference is incredibly small, measured in billionths of a second over a lifetime, but it's real and measurable with the atomic clocks we have today. This has been confirmed with atomic clocks so precise they can detect the difference in the passage of time between two heights separated by just a few feet, about the distance from a table to the floor. This means your head is aging faster than your feet, by about 90 billionths of a second over 80 years. Your brain is experiencing time at a slightly different rate than your toes. We don't notice this because the difference is so tiny, far below the threshold of human perception, but it's there, woven into the structure of space-time. Every part of your body exists at a slightly different point in time, separated by infinitesimal fractions of a second. We are not single points in space-time, but extended objects, spread out across both space and time, and different parts of us experience reality at different rates. This becomes more noticeable in extreme situations, like near black holes or at speeds close to light speed, but it's always present, always affecting everything, just usually too subtle to detect. The universe is richer and stranger than our everyday experience suggests. Fact 87. There are stars that pulsate, growing brighter and dimmer in regular cycles that can last days, weeks, or months. These are called variable stars, and they come in many types with different causes for their variability. Some pulsate because they're old and unstable, having exhausted the hydrogen in their cores and expanded into red giants. Their outer layers expand and contract like beating hearts, driven by changes in opacity and pressure as different layers of the star heat and cool. Some are binary stars where one star passes in front of the other, from our perspective, temporarily blocking its light and causing a periodic dip in brightness. Some are young stars still settling into stable fusion, flickering as they adjust to their new state, their brightness varying chaotically as they accrete material from surrounding disks. One type, called Cepheid variables, has a direct relationship between how long their pulsation cycle takes and how intrinsically bright they are. Longer period Cepheids are more luminous. This makes them incredibly useful for measuring distances in space. By observing how long a Cepheid takes to brighten and dim, astronomers can calculate its true brightness. By comparing that to how bright it appears from Earth, they can determine how far away it is using the inverse square law. These stars are cosmic lighthouses, marking distances across the universe, stepping stones that allow us to build a distance ladder reaching from nearby stars to distant galaxies. They helped us discover that other galaxies exist beyond the Milky Way, that the fuzzy nebulas once thought to be gas clouds in our own galaxy were actually entire galaxies millions of light years away. They showed us that the universe is far larger than anyone had imagined. Fact 88. The Earth is about 4.5 billion years old, but humans have only existed for a tiny fraction of that time. Modern humans, Homo sapiens, appeared about 300,000 years ago in Africa. Civilization, with agriculture and permanent settlements and cities, is only about 10,000 years old, arising independently in several places around the world as the last ice age ended and the climate stabilized. Writing was invented about 5,000 years ago, first in Mesopotamia and Egypt, giving us the ability to record information outside of human memory and pass it down through generations. All of recorded history, everything we have written down and remembered, covers less than 100,000th of Earth's existence. If you compressed Earth's entire history into a single year, with the planet forming on January 1st, humans would appear in the last few minutes before midnight on December 31st. Civilization would begin in the last few seconds. Everything we call history, all the empires and wars and discoveries and achievements, would happen in less than 1 second. The pyramids would be built a fraction of a second before midnight. The Roman Empire would rise and fall in a blink. The entire span from the Renaissance to the present day would be immeasurably brief. This perspective is humbling. It reminds us that we're newcomers to this planet, that the Earth was here long before us and will be here long after we're gone. The rocks beneath our feet are older than any human institution. The oceans and mountains and forests existed for billions of years without us, shaped by processes that operate on timescales we can barely comprehend. We're guests here, temporary inhabitants of a world that has its own deep history, its own story that was unfolding long before the first human looked up at the stars and wondered. Fact 89. When galaxies collide, something beautiful happens despite the violence of the encounter. The gas and dust clouds in the two galaxies crash into each other, creating shock waves that compress the gas. This compression triggers massive waves of star formation, as the compressed gas collapses under its own gravity and fragments into thousands or millions of new stars. These collision-triggered starbursts are some of the most spectacular events in the universe, periods when a galaxy creates stars hundreds or thousands of times faster than normal, lighting up with brilliant blue light from hot young, massive stars. The stars themselves almost never collide because they're so small compared to the distances between them, but their gravitational interactions reshape the galaxies, pulling out long tidal tails of stars that can stretch for hundreds of thousands of light years. Eventually, after hundreds of millions of years of interaction, the two galaxies merge completely, their central supermassive black holes spiraling together and merging as well, creating gravitational waves that ripple through space-time. The starburst fades as the gas is used up or blown away by stellar winds and supernova explosions from the newly formed stars. The galaxy settles into a new equilibrium, now containing 2 or more generations of stars mixed together. Our Milky Way has collided with smaller galaxies in the past, absorbing them and triggering its own periods of intense star formation. And in about 4 billion years it will collide with Andromeda, the nearest large spiral galaxy, creating a new elliptical galaxy that astronomers have already nicknamed Milkomeda or Milkdromeda. By that time, if humanity or our descendants still exist, they'll witness one of the most spectacular shows in cosmic history as 2 galaxies merge in the night sky. Fact 90. Light can be trapped and held in place using carefully arranged mirrors and lasers and special materials. Scientists have built optical traps where photons bounce back and forth thousands of times before escaping, effectively storing light for brief moments, milliseconds, or even seconds. Some experiments have even slowed light down to walking speed or stopped it completely by passing it through clouds of ultra-cold atoms prepared in special quantum states. Light, which normally moves at the ultimate speed limit of the universe, 300,000 kilometers per second, can be manipulated and controlled in ways that seem impossible. This isn't just a curiosity or a parlor trick. It has practical applications in quantum computing and communication, where information is carried by individual photons and needs to be stored and processed without being lost or corrupted. It's also being explored for improved atomic clocks and sensors, but it's also a reminder that even the most fundamental aspects of reality, like the speed of light, can behave in unexpected ways under the right conditions. The universe has flexibility built into its rules, allowing for phenomena that seem impossible at first glance. What appears to be an absolute law, a speed limit that nothing can violate, can have exceptions, loopholes, special cases that reveal deeper layers of understanding. The more we explore, the more we find that reality is richer and more nuanced than our simple descriptions suggest. Every answer leads to new questions. Every discovery reveals new mysteries. Fact 91. The Milky Way galaxy has a supermassive black hole at its center, anchoring the entire structure. It's called Sagittarius, a star, named after the constellation where it appears in our sky, and it has a mass about 4 million times that of the Sun, all packed into a region smaller than Mercury's orbit. Despite its enormous mass, it's relatively quiet right now, not actively feeding on large amounts of matter, producing only occasional flares of radiation, but occasionally every few decades or centuries a star or gas cloud wanders too close, and the black hole tears it apart through tidal forces, creating a brief spectacular flare of X-rays and other radiation as the shredded material spirals inward and heats up to millions of degrees. Astronomers have watched stars orbit this black hole for decades now, tracking their paths year after year with incredible precision. Some of these stars move so fast, whipping around the black hole at thousands of kilometers per second, that they experience significant time dilation, and their orbits show effects predicted by general relativity that aren't present in Newton's gravity. Time moves measurably slower for them than for us watching from Earth. By studying these orbits, scientists have confirmed that the dark mass at the galactic center is indeed a black hole, and have tested Einstein's theory of gravity in an extreme environment where the curvature of space-time is severe. The black hole is surrounded by a disk of hot gas glowing in X-rays, and a dense cluster of millions of stars, all bound by its immense gravity, all dancing to the tune it plays. It's the anchor of our galaxy, the massive hub around which everything else rotates, taking about 200 million years to complete one orbit. Fact 92. There are places in the universe where matter is being created from energy, where something comes from nothing in a way that seems magical but is perfectly allowed by physics. When high-energy photons, particles of light, collide with each other, or with other particles, they can transform into particle-antiparticle pairs, creating matter and antimatter out of pure energy. This happens in the intense radiation fields around black holes and neutron stars, in particle accelerators on Earth, where scientists smash protons together at nearly light speed, and in the aftermath of gamma-ray bursts, the most energetic explosions in the universe since the Big Bang. It's the reverse of what happens in nuclear reactions, where matter is converted to energy, the process that powers the sun and stars. Both processes are allowed by Einstein's famous equation, E = mc², which shows that mass and energy are two forms of the same thing, interchangeable under the right conditions. In the very early universe, when temperatures were incredibly high, in the moments after the Big Bang, matter and energy were in constant flux, converting back and forth in a seething plasma, where particles and antiparticles formed and annihilated billions of times per second. As the universe cooled and expanded, this balance shifted, and for reasons we don't fully understand, matter came to dominate over antimatter, leaving the universe we see today made almost entirely of matter. But the possibility of transformation remains, written into the laws of physics. Matter and energy are not separate categories, they're interchangeable aspects of a deeper reality, different manifestations of the same underlying substance. Fact 93. The orbit of Mercury, the closest planet to the Sun, shifts slightly over time in a way that puzzled scientists for decades and helped confirm Einstein's theory of gravity. The shift, called precession, happens to all orbits to some degree, but Mercury's is the most noticeable because it's so close to the Sun where gravity is strongest. The long axis of Mercury's elliptical orbit slowly rotates, tracing out a flower-like pattern over thousands of years. Newton's theory of gravity predicted some precession due to the gravitational pull of the other planets, but not all of it. There was an extra 43 arc-seconds per century that couldn't be explained. The discrepancy was small but measurable and absolutely real, confirmed by careful observations over many years. Some scientists even proposed there might be another planet closer to the Sun, which they called Vulcan after the Roman smith, though no such planet was ever found despite extensive searches. The mystery was solved in 1915 when Einstein developed his theory of general relativity, which predicted exactly the amount of extra precession that was observed. Mercury's orbit follows not a simple ellipse but a more complex path, because space near the Sun is curved by the Sun's mass, and Mercury is moving through that curved space. This was one of the first major confirmations that Einstein's theory was correct, that gravity really is the curvature of space-time rather than a force acting at a distance. Mercury's orbit is a laboratory for testing our understanding of gravity, and it continues to provide insights today, as scientists look for even smaller deviations that might point to new physics beyond general relativity. Fact 94. There are moons in the solar system with active volcanoes spewing material into space. Io, one of Jupiter's 4 large moons discovered by Galileo, is the most volcanically active body in the solar system, with hundreds of active volcanoes on its surface at any given time. Its surface is constantly being renewed by eruptions, creating a patchwork of colours from different sulfur compounds, yellows and oranges and reds and browns, with almost no impact craters because they get covered over by fresh lava before they accumulate. Some of Io's volcanoes shoot plumes of sulfur dioxide gas, and particles hundreds of kilometers above the surface, visible in images from passing spacecraft. The volcanism is powered by tidal heating, a process where gravitational forces create friction and heat. As Io orbits Jupiter, the giant planet's gravity squeezes and stretches the Moon, flexing it like you might flex a rubber ball in your hand. This flexing creates friction in Io's interior that melts rock and powers the volcanoes. The same process might be happening on Europa and Enceladus, creating and maintaining the subsurface oceans beneath their icy shells. Tidal heating is a way for gravity to generate warmth, keeping worlds active and geologically alive long after they should have frozen solid and become dead, unchanging lumps of rock and ice. It's a reminder that planets and moons are not static objects, not museum pieces frozen in time. They have internal lives, processes and cycles that shape their surfaces and interiors over millions and billions of years. Some worlds are dead, geologically speaking, their internal heat long since radiated away into space, leaving them cold and inactive, but others are alive with volcanism, tectonics, and flowing water or ice, driven by energy from different sources, whether it's radioactive decay, tidal heating, or heat left over from their formation. Fact 95. Space and time can theoretically be bent into loops under certain conditions, at least according to the mathematics of general relativity. These configurations are called closed time-like curves, and they would allow travel backward in time, creating all the paradoxes and puzzles that time travel stories explore. They might exist near rotating black holes in regions where the frame-dragging effect is strong enough, or in certain exotic configurations of matter and energy that probably don't occur naturally. But every solution that permits time travel also seems to require something unusual or extreme, like negative energy density, infinite length rotating cylinders, or wormholes held open by exotic matter with properties we've never observed. These requirements are so extreme that they probably don't exist in nature, or if they do, they're so rare or unstable that they can't be used for time travel. The universe seems to protect itself from time travel paradoxes, a principle sometimes called chronology protection. This isn't a proven law of physics, but it's strongly suggested by the fact that we've never seen any evidence of time travelers from the future, no anachronistic artifacts or unexplainable visitors, and by the apparent impossibility of creating the conditions needed for closed time-like curves with any technology we can imagine. Time flows in one direction, from past to future, and that flow seems to be fundamental to how reality works, built into the structure of causality itself. Causes precede effects. The past is fixed and unchangeable, and the future is open and undetermined. This might not be an accident or an arbitrary rule, but a deep feature of the universe, perhaps related to the increase of entropy and the arrow of time. Without this one-way flow, cause and effect would break down, and the logical structure of reality might become impossible. Fact 96. The light from some stars has been travelling for so long that the stars themselves no longer exist in their original form. The light we see tonight from distant galaxies might have left its source when the universe was young, when the first galaxies were just forming from clouds of hydrogen and helium, before heavier elements existed in abundance. By the time that light reaches us, billions of years have passed. The star that emitted it might have long since exhausted its fuel and exploded in a supernova, scattering its atoms across space to be incorporated into new stars and planets. Or it might have quietly faded into a white dwarf, a dense ember slowly cooling over trillions of years. But its light continues on, a messenger from the past carrying information about what the star was like when that light began its journey, what elements it contained, how fast it was moving, how hot it was. We're seeing into the past every time we look at the night sky, watching a universe that no longer exists in the form we observe. The stars we see are ghosts, images of things that were but are no longer, or at least no longer in the state we're seeing them. This is the nature of light and distance in the universe. Information takes time to travel, limited by the speed of light, and by the time it arrives, the source has changed or vanished or evolved into something new. We live surrounded by echoes of the past, light from dead or transformed stars still finding its way to our eyes, photons that have travelled across the void for eons, finally ending their journey when they strike our retina or a telescope's detector. Fact 97. The asteroid belt between Mars and Jupiter is not densely packed like movies and television shows often portray. The asteroids are spread out over such a vast volume of space that if you were actually in the asteroid belt, flying through it in a spacecraft, you probably wouldn't see another asteroid with your naked eye. They're separated by millions of kilometers on average, tiny specks scattered across an enormous volume. The total mass of all the asteroids combined is less than the mass of Earth's moon, maybe only 5% of the moon's mass. Most of that mass is contained in just a few large objects. The asteroid belt is the debris left over from the formation of the solar system, material that never coalesced into a planet because Jupiter's powerful gravity kept stirring it up, preventing any large body from forming and occasionally sending asteroids into planet-crossing orbits where they could collide with the inner worlds. Some asteroids are large, hundreds of kilometers across, essentially dwarf planets. Most are small, just rocks and boulders tumbling through space, fragments from ancient collisions. They collide occasionally, breaking into smaller pieces, slowly grinding themselves down over billions of years. Some asteroids have been captured by planets as moons, like Mars's two small moons Phobos and Deimos, which are probably captured asteroids. Some have been flung out of the solar system entirely by gravitational interactions with Jupiter or other planets, and some have crashed into planets, including Earth, bringing water and organic molecules in the early days of the solar system, or causing mass extinctions when they struck at the wrong time. The asteroid belt is quiet now, mostly empty space with occasional rocks drifting through it, a graveyard of failed planets, but it has shaped the history of the solar system in profound ways. Fact 98. When you look at the stars, you're seeing nuclear fusion happening in real time across vast distances. Every photon of starlight was created in the core of a star where temperatures and pressures are so high that hydrogen atoms are being fused into helium, releasing energy in the process through the conversion of a small amount of mass into pure energy. That energy works its way outward through the star in a random walk, taking thousands or even millions of years to reach the surface as it gets absorbed and re-emitted countless times by the dense material of the star's interior. But once it reaches the surface, it shoots out into space as light, travelling at 300,000 kilometers per second. Some of that light, after travelling for years or centuries or millennia across the emptiness of space, enters your eye and triggers a chemical reaction in your retina, which sends an electrical signal to your brain, and you perceive the star, a point of light in the darkness. You're connected to that distant sun by a chain of photons, particles of light that have crossed the void to reach you, bridging distances that would take human lifetimes or generations to travel. The light carries information about the star encoded in its wavelength and brightness, its temperature and composition and motion. It's a message written in the language of physics, a signal sent out blindly into the universe, not for any particular receiver, but simply because that's what stars do. And when you see it, you complete the circuit. You receive the message. You're part of the universe observing itself, matter and energy arranged in such a way that it can look outward and wonder, ask questions, seek answers, find beauty in the patterns of light. Fact 99. The universe might be just one of many in a vast multiverse, an infinite collection of separate realities. Some theories suggest that our Big Bang was not unique, that other universes are constantly being created through processes like eternal inflation, where different regions of space stop inflating at different times, each becoming its own separate universe with its own laws of physics and constants of nature. Some of these universes might be similar to ours, with stars and galaxies and planets. Others might be radically different, with different numbers of spatial dimensions, different particles and forces, different values for fundamental constants, like the strength of gravity or the mass of the electron. In some universes, stars might never form because gravity is too weak or the expansion too fast. In others, everything might collapse immediately because gravity is too strong. In others still, life might be common, might take forms we can't imagine, might have evolved and spread across galaxies in ways we dream about. We have no direct evidence for the multiverse, and it's not clear if we ever could, since by definition other universes would be causally disconnected from ours, separated by barriers we can't cross or see through. But the idea emerges naturally from certain theories, particularly from inflationary cosmology, which solves several problems about the early universe, and from string theory, which suggests our universe might be one solution among many possible solutions to the equations. It's a humbling and dizzying thought that our entire universe, with all its billions of galaxies and trillions of stars and countless planets, might be just one bubble in an infinite foam of universes, one story among endless stories, one reality among endless realities. We might never know if it's true, but the possibility expands our sense of what reality might be, challenges our assumptions about uniqueness and specialness. Fact 100. After all these facts, after all these journeys through space and time, through the quantum foam and the hearts of stars, from the beginning of the universe to its possible endings, perhaps the most remarkable thing is that we can understand any of it at all. We're small creatures on a small planet orbiting an ordinary star in an unremarkable region of an average galaxy, evolved to navigate our immediate environment, to find food and shelter and companionship in the forests and savannas of Africa. We weren't designed to comprehend the universe at its largest and smallest scales. Our brains evolved over millions of years to track prey and avoid predators, to recognize faces and learn languages, to navigate social hierarchies and pass on knowledge to our children, not to grasp space-time curvature or quantum superposition, or the nature of dark energy. And yet, through observation and experimentation, through mathematics and reason, through the collective effort of thousands of scientists over centuries, we've managed to map the cosmos. We've measured the age of the universe to within a few million years out of nearly 14 billion. We've calculated the distance to galaxies billions of light years away. We've discovered that space and time are flexible, that matter and energy are interchangeable, that we're made of atoms forged in the cores of dying stars. We've learned to read the messages written in starlight, to decode the echoes of creation preserved in the cosmic microwave background, to detect gravitational waves from colliding black holes. This ability to understand, to know, to discover, might be the universe's way of understanding itself, of becoming aware of its own existence and nature. Through us, and perhaps through countless other beings on countless other worlds, scattered across space and time, the cosmos becomes conscious, aware of its own existence, capable of wonder and curiosity and love. That's what you are, in the deepest sense. You're not separate from the universe, observing it from outside. You're the universe, awake and aware, looking back at itself with curiosity and awe. And in this moment, as you drift towards sleep, you carry within you the knowledge of stars and galaxies, of time and space, of quantum fields and gravitational waves, of the vast and beautiful reality we're all part of. Rest now, knowing that you're connected to everything, that the atoms in your body have travelled across space for billions of years to be here, that you're made of stardust and quantum foam and cosmic time, you're home in the universe and the universe is home in you.